Another extension of implicit differentiation is logarithmic differentiation. We use logarithmic differentiation when there are variables in the exponent and we're not dealing with just simply an e to the x function. So for example, suppose we wanted the derivative of 2 to the x, and of course this will work for any base other than e to the x. So we say y equals 2 to the x. Step 1 in logarithmic differentiation is we take the logarithm of both sides. So of course we get log y equals x log 2. And of course log 2 is just a constant. Now we'll take a derivative now that we've taken the logarithm. So y prime over y equals log 2. So y prime equals log 2 times y equals log 2 times 2 to the x. And that is the derivative of 2 to the x. Anytime that you take the derivative of any base to the x, what you get is the logarithm of that base times the original function. And of course, the only function where you don't get that out in front, that factor out in front, is when you're taking the derivative of e to the x, which is simply e to the x, and the log of e is 1. Now suppose we have this more complex function, x to the x. Well, we can't use a power rule for this. This is actually a very complex function. So we can use logarithmic differentiation. So if we take a logarithm, we get log of y equals x log x. Now when we take the derivative, y prime over y, on the right side we have a product, so we have to use the product rule. So we get derivative of x, which is 1 times log x, plus x times the derivative of log x, which is 1 over x. And so what this is just log of x plus 1. And so y prime equals y times log of x plus 1 equals x to the x times log x plus 1. And that is the derivative.